So this is a group effort, and it just... Can you hear me? Yes. Okay, this group effort took place just in the last few hours of this meeting. It wasn't prepared in advance. And of course, as you probably all know, heart disease is one of the leading killers of Americans and of humans all over the planet. And arterial plaques cut off blood supply to the coronary arteries, causing the heart muscle to die, and that's called a heart attack. So the arterial plaques grow in the wall of the artery, and as they do, they puff out the wall and restrict the flow of blood through the wall, and that restricts the flow of blood to the heart muscle. So our proposal is to build nanorobots that will travel through the bloodstream. And let's see, I think I should go to the next slide here. So, okay, so what's the current state of the art? Right now, either you cut open the person's chest and start operating on the heart directly, which is dangerous and very expensive. And another choice is to stick a catheter in a vein in the leg and run it all the way up and hopefully direct it to the right spot and put in a stent that will push the artery open. But this has often resulted in complications because it injures the arterial wall as you stretch it out with the stent. So it's not a desirable way to go either, and it's also quite expensive. But currently we can see where the plaques are using MRI and X-ray tomography. And so we know where they are, and our idea is that we can inject these robots into the bloodstream and then activate them at the location of the plaque using 2-photon near-infrared radiation to trigger them to be active when they get to the location of the plaque and not to be active elsewhere. So we've got propulsion units on the sides of the robot. It's got a rotary motor inside that turns like a blender blade that chews through the plaque, and it has detectors that detect when it reaches the edge of the plaque so that it doesn't cut into the healthy tissue, and it spews out tiny little pieces of the plaque behind it, and those tiny little pieces will get treated by macrophages in the bloodstream and eventually removed from the circulation either through the gut wall or be digested by the macrophages. So the phases of our proposed strategy are build this nano plaque digger based upon previous examples of nanotechnology that already exist in the lab in other biomedical application projects. For example, Tour's use of the Furber rotary motor drive claw that cuts into membranes. We're just going to build a bigger claw that cuts more than just membranes. It cuts up the body of the plaque itself. And then nanoparticle drug delivery. Well, these little motors are nanoparticles because they're so tiny. They'll be coated with polyethylene glycol, which has been tested in a number of nanotechnology labs to keep the immune system from reacting with the nanoparticles. And we'll use an external 2-photon light source for near-infrared radiation at the plaque to activate the digger when it gets in proximity of its target. So, the milestones and budget. Number 1 milestone, build a device that works. Number 2, test it in a living pig. Number 3, start clinical trials in humans. And of course, clinical trials are expensive, so by that time we'll be partnering with some big pharma that will have lots of money to invest. And beyond that, FDA approval, and then count your returns. Thank you.
Questions, suggestions? Let's see. So is there concern about the particles that's spewing out back into the blood, the particles of the plaque that are getting shoot up?
That is something that we will be testing to see exactly if we have to passivate the particles in some way, because the 7-keto cholesterol that makes up the bulk of the plaque is what initially started the immune reaction that built the plaque in the first place. There will be some tweaking and some testing of variations on the system in order to reduce the risk of that.
Okay.
Judges, Stephanie.
Do you have a particular particle size in mind, and how is it going to localize to the sites of plaque buildup?
We're going to localize it with the 2-photon near-infrared light source. So if first we locate the plaque with X-ray and MRI, and say it's right here on this side. So we'll then take one infrared light source like this way and one this way. So the 2 photons, where they merge, create enough energy to activate the robot to turn on.
Oh, so how are you going to get the robot to the site?
Injected into the arm.
So it's going to be going via systemic circulation?
We're going to inject thousands of them into the arm. It's going to circulate throughout the body, but it's only going to turn on where the 2 light beams intersect.
So how does the chopper know the difference between the plaque and something else?
We have sensors on the front of it. You can't see it in the picture, but sensors on the front test for stiffness, and the plaque is stiffer than the normal tissue.
And the robot is how big?
It's nanoscale. It's very tiny. It's small enough to get through capillaries without clogging them. So maybe 3 microns.
So how realistic is it? Like what exists right now that's a comparison to?
I'll have to defer to my technology partners here. Do you want to say a little bit about what the technology predecessors are?
Approximates this. It's already working.
Sure. I don't have a mic for the camera. So these nanomotors are really small. They're small molecules, but if you want to functionalize it with a polymer, you can make it as big or as small as you want. So nanoparticle drug delivery, if you're thinking about getting to tumors, it needs to be less than like 20 nanometers or 30 nanometers. But in this particular case, this cartoon represents a motor that it's pegylated. So you can, like I said, you can try to put it in the stealth mode and get it to be as big or as small as you want, and to try to put targeting groups on there too, so you can try to specifically get there. The crux of the argument, though, is to try to, it's what Stephanie was hinting at a second ago, which is how do you necessarily target specifically plaque relative, right? And so we were proposing to have some sort of density sensor. So the plaque is thicker and denser than the other tissue, the smooth muscle tissue that lines the artery. So if you could sense the difference in density in that area and also have the 2-photon light source irradiate exactly where you want to treat, then you could, in principle, start the propeller motion and start digging in. And so that's been done before with cancer cells. People have used these molecular motors to dig through the membrane of a cancer cell. So the proof of concept has been shown. This was like in a Nature paper a couple of weeks ago. The question is, how can we then turn that into a robot or something that can selectively find these different sites? And so that's the gist of it. So it's tunable through synthetic chemistry.
Any more questions from the judges? How does it get out of your body then, once you put all these in?
Natural excretion, right? So if you're using polyethylene glycol, it's biocompatible, it's FDA approved, it breaks down, you can clear these things. So it's all directly related to size in terms of clearance. So if it's less than 5 nanometers, then it goes through the kidney. If it's bigger than 5 nanometers, it generally ends up in the liver. But you can look at pathology and toxicity, and you can find that these things, especially lower concentrations, they're way less toxic than other drugs that you might take, right? So one of the things that he hinted at in the beginning was that people take drugs to lower their cholesterol levels, but that doesn't break up the plaque. That just prevents further plaque formation, right? So you're treating the problem, but you're not curing the problem. So this is a way to look at trying to cure the problem and using physical forces of a motor, which turns out to be a lot stronger than people thought. And this thing is just whipping around, millions of times per second. So you physically try to disrupt the plaque formation.
Okay,
Any other questions from the judges? If not, we'll go to William.
Could you say a bit more? I don't have a picture of how this thing is supposed to anchor onto a potential substrate, and then how is this robot? What's the mechanism by which it tests the stiffness or density of the material, and then how does that actually communicate to the rotor to turn on?
So one of the things it's a great question. One of the things we were thinking about is obviously if there's a difference in the rigidity or robustness of that particular region.
How does it anchor onto a potential substrate?
So right now we don't have anything built into the mechanism that would anchor in, right? That's obviously what you would want, but if there's somebody in the room that actually knows more about arteriosclerosis and plaque buildup, and if there's any receptors or biomarkers on the surface that we could target for, right? You can use a peptide or some ligand to bind, that would be ideal, right? So that's what they did in this nature study with the cancer cells, is that they had specific receptors that they could functionalize the motor with, and it's like it grips basically that receptor, and then it starts to rotate, and it just physically ripped the membrane apart. So that would be ideal, but in this particular case, we were thinking about having protective vesicles that are also activated through this two photon source, and then have that be a release mechanism and then so once you have the nanobots localized in that region, you're only irradiating that region, and so they're going to start digging away.